So when it comes to linearizing this population growth equation, what we want to try to do is make it so that the right-hand side, after we've solved this equation for its subject, and we have the hunch that the subject in this example is going to be z, the population of zebras and thousands, on the right-hand side we need a sum of two terms, and in one of those terms we have a variable factor, namely the x, and in the other term we do not, so the other term is constant. So that's what we're looking for when we're trying to linearize an equation, is a sum of two terms, one of which has the variable factor in it, and the other which does not. And before we can get that in our equation, we've got to deal with these nasty parentheses. We can do that by distributing, as Quinn says. So let's distribute. Multiplication across addition and subtraction distributes. And so I end up with, on the left-hand side, z. On the right-hand side, zc, the carrying capacity, times 1, minus zc, the carrying capacity again, times e to the minus kt. So we did the distributing part. Now, are we any closer to this matching y equals mx plus b? What did you say, a group that worked on K4? X, right? X is the other variable that we want to ultimately figure out how what x should be in order to linearize this equation. But the other variable that we're interested in our data is t. So whatever x is, it should be some expression which depends on t. So what expression on the right-hand side of our equation down here at the bottom depends on t and could play the role of our variable factor x? Gotcha. So this whole thing sitting right here, it has our variable t in it. So chances are we're going to try to match that up with the variable term in our linearized equation. Somehow, minus z e to the minus kt, we're going to match up with m times x. Where m, our slope, remember, is a constant parameter, and x is something variable. Let's start with the slope. What does it look like in this term here is going to play the role of the slope m? Zc. Remember, this e, according to the order of operations, this e to the minus kt, this power happens before it gets multiplied by zc. So zc is not getting multiplied by e. Zc is getting multiplied by e to the minus kt. So when we look for our slope, we're going to take just zc, because that's the constant multiple in this term. And then the e to the minus kt becomes what? It becomes our x. Then what's b? Yeah, it's this one thing we didn't account for yet. It's the b out front. So what does this mean in total? It means that we're going to linearize, in part A, we're going to linearize this growth equation by plotting the transformed variables y equals z and x equals e to the minus kt. And that's going to linearize this equation. And notice it also satisfies the other thing that was asked for here in the problem, which was we need to be able to somehow determine the slope. From the slope, we need to somehow determine the carrying capacity of this system. Well, what's the slope? It happens to be equal to exactly the opposite of the carrying capacity. So this satisfies the requirements we were looking for. If we were to run a linear regression on these linearized variables, z versus e to the minus kt, and we would find the slope of that, the slope would be minus the carrying capacity of the ecosystem. So here is a set of variables that linearizes our equation. And before we move on to the next example, let me ask you, why was it important that we know the value of k in this problem? Why do we need to know the value of k in order to make this work? down at the bottom here in our capital X, we have a k. If we didn't know what value k had, if this was unknown, then we would have no way of transforming our t's into capital X's in order to make this step happen. In other words, as Andrew says, we would have more than one variable subsumed inside of our x, which we don't want. Right? We're not working with multivariable regressions, not in this course. We could do that in another course, but not for us. So we can only linearize with k belonging to one of our linearized variables, and we can only do that if we know the value for k. And in part A, that's what we do. We happen to know in part A that k is equal to 0.2 reciprocal seconds. So that's how we get away with this linearization. It's also why we would choose a different linearization in part C when we don't know the value for k, but we do know the value for z sub c, the carrying capacity. Okay, so you figure out what Excel tells you. You take your data, you transform your data. In other words, you make your y-axis data all your z's. You make your x-axis data the values of e to the minus kt for all of your t's. And what pops out of Excel is an equation that looks like z equals minus 0.3743 times e to the minus kt plus 1.7186. Now, we have a slope and we have an intercept. And according to the slope, if this is our m, how do we find the value of the carrying capacity from this slope? Well, according to our parameters, m was equal to minus the opposite of the carrying capacity. So all we have to do is set minus the carrying capacity equal to this number. 0.3743 equals minus zc. From whence we can find out that zc, the carrying capacity of this ecosystem, is 0.3743. And looking back at the units, that's 0.3743 thousand zebras. And you might do that only because I mentioned in the question that we're going to try to use the slope to determine a value for m, for the carrying capacity, rather. But notice we could also have gone the other way and use the intercept. Because the intercept is actually equal to the carrying capacity, we actually get a different answer, a different match, if I match up the intercepts of this equation. That according to the intercept, the carrying capacity is 1.7186 thousand zebras. So that's one of the issues, by the way, one of the problems with knowing one of the parameters in a linear regression and trying to find the other is that you might get competing answers. In an exam situation or something, I would take whichever one of these you match up, because either one of them is honest to the way that we linearized this equation.